Thanks, Dick, for a wonderful introduction. Yeah, we worked together for 7 years. That's 49 dog years. But anyway, so just wanted to tell you a little bit about a few things that are actually on the unofficial Google Data Science blog. By the way, we now also have googledatascience.com. If you do that, it will directly forward you to the unofficial Google Data Science blog. The reason for this is that it got too hard to tell people why we call ourselves the unofficial Google Data Science blog. It doesn't matter. It's probably all fine. Anyway, so this is just a condensed version of some of the things that are in one of the posts there that I wrote back in January. So those of you who are reading the blog, thank you very much, and I apologize for regurgitating some of this stuff. OK, so this is kind of like a hypothesis here that I'm making an argument. You guys can disagree with it. That the scalable web technology is what spurned a lot of data science. It was true for me personally, and I think it was true for lots of people. I'm not saying it's exclusively the case, but scalable web apps and web technology and apps gave rise to what I'm calling LSOS, which is large-scale online services. These are basically everything that we see today. Lyft is included, Google is included, Facebook is included, lots and lots of businesses and services that we use all the time, each of us without thinking anymore. And what was interesting about it, which happened, I guess, in the late 90s, whatever, is especially if you don't have any physical goods that are moving, then the marginal cost of serving an additional user is basically going to zero. It doesn't, the variable cost is small. You may have to spend a lot of money building up a data science team, building up the technology, but once you have it in place, it's just, you can just scale volume very, very cheaply. And that led to fierce competition to get user engagement, because if you can do this, then so can your competitor. It's all about trying to attract people, trying to get them there. And so there's a need for constant improvement because there's this fierce competition going on. And that leads to us having lots and lots of data and experimentation and analysis. And then, of course, with all this data comes the need for inference. And that means for you and me, right? So this is good stuff. We're happy about this. OK. So I used to work in speech recognition in grad school, at least briefly. And there was a saying back called, there's no data like more data. This is from the 80s. And so, more data is actually better for lots of things. In particular, there are lots of inference techniques, modeling techniques, what have you, that improve automatically with the more data you throw at them. They're data hungry. And so I like to use this term SMOD, which is a simple matter of data. Right? You want to work with problems where if you throw more data, it just gets better. It makes everything easier. And if you work in one of these big companies, you have more and more data. And many of you are data engineers. I mean, your job is to bring us the data and feed it to these beasts, hungry beasts, and everything gets better. Live randomized experiments are also pretty important because most business questions are, and this took me only 10 years to understand this, but most business questions are actually questions of causal inference. People want to know, does A cause B? That's really what they want to know. So how do you get causal inference? There's lots of complex techniques in many situations, but the best case scenario is if you can do a randomized experiment. Now, Nick went into situations where that's not doable in certain situations because there's this interference. But assume here, for the sake of this talk, you can actually silo off users, and therefore you can run randomized control treatment studies. OK, so that's the gold standard. Great. The more data you have, the better it is, the faster things will go. And my boss at the time, and now again my boss, Diane Tang, and others wrote this paper called Overlapping Experiment Infrastructure, More, Better, Faster Experimentation. You can read about it. It's what made the ad system at Google, the search ad system, so efficient because we were able to run large amounts of experiments very, very fast. OK, all great. So given enough data, any true effect will become statistically significant. I assume you guys all know a little bit about hypothesis testing, so I won't belabor too much. But if you have enough data, if the effect is true, eventually you'll be able to determine it. And so I will say that statistical significance is SMOD. It's a simple matter of data. If you have enough data and this effect is true, you'll get significance out of it. That's pretty comforting. Let's see. Excuse me, I got to keep an eye on the time. OK. So then there's, of course, practical significance. And again, this is probably well known to most people, but just give me a slide here. Statistical significance is about, is basically answering the question, is the difference I'm seeing in my experiment and control, let's say, is it likely due to chance, or is this something I can sort of believe? That's what statistical significance is about. It's about uncertainty. Practical significance is something else. It says, well, does anybody care? Does it matter? What will I do with it? And it is about the purpose of what the conclusion you're going to draw. So maybe business objectives or what have you, that kind of thing. So they're quite different in terms of what you're trying to do. So let's take a quick example. OK, so since I was coming to Lyft, I made up this slide. Are Lyft users taller than Uber users? So imagine I do a hypothetical study. And essentially what I do is that I do this study and assume everything is kosher, I did everything correctly. And it turns out that the difference in average height of Lyft users versus Uber users is 0.01 inches plus or minus 0.002 inches with 95% confidence. So that is to say that it's statistically significantly true that Lyft users are slightly taller than Uber users, OK? So then out comes the newsflash says, oh, Lyft users are significantly taller. Now, is this true or is this false, right? I mean, it's kind of true and it's kind of false. It depends what you mean. Statistically significantly taller, yes. Practically significantly taller, no question. I mean, I don't think we'll be getting bigger cars for Lyft users because of this, right? So it's not going to matter. OK, so statistical significance, as I said, was SMOD. Given enough data, any true effect will be statistically significant. But in the world of data, in all our data, it's replete with barren truths, truths that don't lead anywhere. They're true, but who cares? We need better hypotheses. Mere difference is not super interesting, right? Just the fact that they're taller by some amount isn't interesting. OK, so now I'm going to go through my logic here, which probably is flawed, but let's see if you can see it. So imagine I've got some important metric m, and I have a hypothesis. I say that, OK, this metric in treatment minus the metric in control has to be bigger than delta. And the reason I put in delta there is because I don't want to go back to the previous thing where something is trivially small. So delta is chosen so that it's practically significant. It's the minimal practical significance bar, let's say, for what metric m is. OK, so here's the logic. Statistical significance is SMOD, so it's just about data. I have tons of data because I have maybe millions, billions, whatever, lots of users. Therefore, a small experiment will show if my hypothesis is true or not with 95% confidence. Is that true? Can I conclude that? I guess some people are suspicious. OK, so it's not always true, right? But let's imagine if it were true, what would that mean? I have tons of data, right? So everything can be answered. If it's true, I will very quickly know that it's true. If this were true, the implications are rather disturbing for you and me. Why? OK, so there's no need to do experiment sizing because 1% is small enough. It's peanuts. Making it 0.7% is not interesting, so that's fine. No need to be sophisticated about estimating statistical significance because the error bars are too small to care, right? So at Google, for example, we have a cottage industry where if somebody puts up a chart and doesn't put error bars, somebody in the audience says, where are the error bars? But in this case, sometimes they're too small to matter, right? And so that's a good answer, by the way, sometimes. And so any useful hypothesis can be quickly tested, so that's great. But then you know what? Guess what? PMs are going to run everything because they're the ones coming up with the hypotheses. We can probably fire all the data scientists. We may still have to keep the data engineers, so don't worry. Those of you who are coming from the data engineering side, the SF data science people have to be worried. At least we don't want to waste the data scientists on experiment design and analysis because there's nothing really there to do. It's all relatively trivial. So this does happen sometimes. I actually was interviewing somebody from a well-known online movie downloading site, which I will not describe. But anyway, and I heard that this is what they don't think of, and that's fine, right? They don't think that experiments are about statistical uncertainty. For them, it's all simple and trivial. Luckily for the rest of us, it's not, because if it were, we'd be out of a job. So yes, statistical significance is simply a matter of data, but delta is often so small that we still don't have enough data. Now, that seems contradictory, but we'll get to in a second. Not even when you have billions and millions of users. And why? Because it turns out because every observation has very little information towards answering the question you care about. OK, so let's see. So now just a little bit of math, but nothing fancy. So imagine the simplest of cases. You got two populations. There's the control population with a mean and a variance. And then the treatment population has the mean plus delta and the same variance. OK, so the effect size, traditionally speaking, if you guys study statistics, it's for a t-test, two-population sample setup, is the difference in population means as a fraction of the standard deviation. OK, that's kind of a traditional way to describe this. So, and an effect size of 0.2 would be considered small. My sister's a psychologist, and they are not interested, even they are not interested in 0.2, right? OK, sorry, she's in San Diego, but anyway, all right. So statistical significance is SMOD. So going back to this, what is it? So if you have two samples, and let's say n tilde is the harmonic mean of the sample sizes, you don't have to worry about the details here, and alpha is the type 1 error rate, beta is the type 2 error rate, then you get statistical significance is if this condition is true, which is very much to say if you stick in typical values of 0.05 and 10%, you say if the effect size times the square root of the sample size, the pooled sample size, is greater than some amount, right? So if I get enough data, that means n tilde is big enough, I will be able to get statistical significance regardless of how small E is. But it's also true that if E is super duper small, then I need more n tilde, right? So that's a trade-off here. OK, now we'll go to the notion of practical significance. So here I'm going to define this term for which I'll become famous someday called effect fraction, which is to say it is the size of the effect, the delta, the difference in group means, divided by the mean, not by the standard deviation. OK, so now who the hell cares? The reason is that this is how most people think about what they do. If I have a metric, I say I got a 2% increase in my metric. Let's say it's the number of the ETA, let's say the Lyft, how long it takes somebody to show up. It's 2%, not a fraction of the standard deviation, but 2% of the mean. This is what normal people, that is to say non-statisticians, think about when they think of things. And that's why I'm calling it effect fractions. It sounds like effect size, but it's not really that. OK, so in this context, a 0.02% can be practically significant. Depends what you're doing. So in the Google search ads world, they're making something like $50 billion a year. 2% is nothing to sneeze at. It's more than what they would pay us. So that's kind of, that would be a big deal. OK, so it depends on what you're doing. And I think in most cases, if it's an important metric for Lyft, whatever, I think a 2% change would be a big deal. OK, going back to this statistical significance and practical significance in a different way. So imagine F was the effect fraction. E was the effect size. The ratio between these is the coefficient of variation, which is to say sigma divided by mean. It's the standard deviation divided by as a fraction of the mean. OK, so with some advanced math, we can see that effect size is the effect fraction divided by the coefficient of variation, which is to say the bigger your coefficient of variation is, the more it's going to shrink your effect size. OK, so this coefficient of variation comes to be something very important. And the bigger it is, the harder it is for us to do what we need to do. OK, so what I'm going to make the case is that the bigger coefficient of variation makes us information poor. OK, well, obviously because it shrinks our effect size, so therefore it gets harder to make statistically significant discoveries. But it's another more direct way to think about it is that the coefficient of variation is a measure of how much information observations have towards measuring a mean. So for example, if I was going to take the sample average to estimate a mean, the standard deviation of my estimate would go as square root of 1 over square root of n. And so the fractional error that I have in estimating the mean, mu, is the coefficient of variation divided by square root of n. So it comes up here, right? So the bigger this is, the more percentage error I'll have in estimation. It gets pretty fundamental that way, right? OK, so now let's think about coefficient of variation when you have rare events. Suppose I have, I don't know, pick something. People click on ads, which is a rare thing. I don't know why they do it, but it keeps the lights on. Or why people open a Lyft app. Well, it's probably a rare event, so to speak. Or maybe, I guess a better case would be somebody clicks a like button, right? So there's lots of interactions, but very rarely there's a like click or something like that. So now imagine y is whether there was a like click or not. And it's a Bernoulli random variable, binary, with probability p. So the coefficient of variation, if you calculate it, it's just the binomial probability, square root of that, divided by the mean. And that turns out to something like 1 over square root of p. So if p is small, a rare event, this thing gets bigger and bigger. Okay? So your coefficient of variation is essentially the rarer the event, the larger the coefficient of variation, which going back will shrink your effect size and therefore make life difficult for you in experiments. So rare events are, rare events and small effect fractions are kind of part of the landscape of large-scale online systems, often services. So let's go through the logic here, and I'm getting close to the end here. So low marginal costs mean the business can rely on monetizing rare events. What do I mean by that? So take something where there's a service, it's a glorious service, and pick your favorite glorious service, where most of it is free. It's just free. So how the hell does this happen? Well, because there's a few rare events that monetize things, that pay for the whole show. Okay, so in search ads world, search, which is incredibly expensive to run, is all free. But once in a while, somebody clicks on an ad, and that makes everything work. That funds everything. Imagine I've got a personal finance website. It's free. You can do all sorts of stuff. You can upload things. You can check stuff out. And then once in a while, I might sell you a financial product. And it's a pretty rare event, like a loan or a credit card or whatever. And that will keep the lights on for everything else, right? So it's a rare event that does it. Or a photo storage site. I mean, I don't know what Shutterfly's business model is, but I'd imagine if I ran a photo storage site and I said, you got to pay me $10 a month, nobody will do it. But if I say it's free, okay, free, everybody loves free. But once in a while, I'll sell you a photo book. This is like $60 for your, I don't know, kid's birthday or something like that. And so I won't do it very often, but I'll do it just enough that it will keep everything going, right? So this is all possible because of the scalable technology and low marginal costs. Okay, the other thing that happens is that because there's low marginal cost, that is to say, it doesn't take anything to, once you've built the thing, it doesn't take much to service more and more users. Any growth that you can push through by making changes or what have you is going to hit the bottom line because you're not moving bricks around. It's just all virtual, and so you'll make more money if you can get more engagement, more growth, or whatever your metric is. And so that's why these large-scale online services, they often care about rare events, and they care about small effect fractions, both of them. OK, final slide. But there's some poetic justice here, perhaps, right? And this is my hopeful or whatever enigmatic slide. It says that, so large-scale web tech drives marginal costs down. So that means it's very easy to serve more and more people. It enables these online services, very large scale, with lots of users, lots of experiments, and they're data rich. They've got tons of data because they're very scalable. The low marginal costs enable a business model which relies on rare events and cares about small effect fractions. Okay? So that makes every observation that they have, they've got tons of observations, but it makes every observation information poor relative to what they care about. So therefore, they have to run these massive experiments that social scientists don't have to run because they're much more, in this context, we're much more information poor. Now, luckily, these large-scale online services do have lots of users, so there's some kind of balance there. You have tons of users, but you never have enough, right? It's kind of like you always want more. And that's kind of the conclusion of my slides here. So I hope this I hope I succeed in at least giving you some connection, however tenuous, between business models and statistics in terms of how certain business models will promote a certain kind of business and therefore create certain problems that tie back to it. And now you're going to introduce. Okay, thank you.